Okay, so next we're going to take a look at how to deal with a pure parallel circuit and calculate not only the equivalent resistance, but also the voltage drop through each resistor, or across each resistor, and the current going through each resistor. So here's a pure parallel circuit. And at first when you look at this, you might be like, whoa, that doesn't look like parallel, that looks like a hybrid circuit. But actually, let's follow the current coming out of the battery here. So the current comes out of the battery, goes up and around over here, and then it meets this junction. In this junction, it can either go through the 30 ohm resistor, or it can skip right to this area, because after all, this is just a wire which has no resistance. So it either goes to the 30 or skips right to this area. Well, when it skips right to this area, then it has a choice of either going through the 10, which would then bring it down here and back to ground, or through the 15, which would bring it down here and back to ground. And of course, if it went through the 30, it's down here and back to ground in any case. In other words, you can think of this as simply moving this wire over here so that this little junction right here simply stems out all from this, and then the 10 ohm resistor would curve out like so, and the 15 ohm resistor would curve out like so, or maybe back over this way. However, either way, you're dealing with three resistors that are in parallel. So this is a pure parallel circuit. So the first matter of business is going to be calculating the equivalent resistance. So you end up calculating the equivalent resistance by, well, using the formula and first writing your givens. So remember that the formula for calculating the equivalent resistance is 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 for three resistors in parallel. Well, so plug them all in. So you can do this one of two ways. You can either just directly plug this into your calculator, do 1 over 30 plus 1 over 10 plus 1 over 15 in your calculator. Make sure to use parentheses in the appropriate place. And then make sure to take 1 over the result, because after all, what we're looking for is in the denominator. So the equation was like this, and this was in the denominator. So if you plug this in directly into the calculator, you need to do 1 over your result. You need to take the inverse of your result. In other words, the inverse of the equivalent resistance is equal to the sum of the individual inverses, because after all this, we haven't plugged in 30 ohms, we've plugged in 1 over 30 ohms, and then we've plugged in 1 over 10 ohms and 1 over 15 ohms. Add them all together, and you get 1 over the result that you need. And you might wonder, it's like, well, why can't we just flip this right back up right now? Well, and then that would be 30 plus 10 plus 15. Well, that would be the formula for series. That's not the formula for parallel. You're going to get something very different by doing this. You're not going to get 55 ohms. You'll see what we get. So doing this algebraically, and which is how we're going to do it, you would need to find a common denominator. Well, actually, there's already a common denominator here. 30 divides both 10 and 15. So what we want to do is we want to turn this 10 ohm into 30 ohms, and we need to turn the 15 ohms into 30 ohms. Well, to do that while still keeping the fraction the same thing, what we're going to do is, well, 1 over 10 is the same thing as 3 over 30. In other words, we're going to multiply top and bottom by 3. Why 3? Well, 3 was what we needed to multiply the bottom by in order to turn 10 into 30. Well, whatever you do to the bottom, you got to do to the top if you're trying to keep your number the same. So we multiplied top and bottom by 3. Well, with 15, you need to multiply top and bottom by 2. So 1/15 is the same thing as 2/30. So that works out. We have a common denominator now. And the reason this all works is because when you're adding fractions together and you have a common denominator, all you need to do is just add up the numerators. After all, if you have 1/30 of a piece of pie, or sorry, if you have 1/30 of a pie, and you have 3/30 of a pie, and you also have 2/30 of a pie, well, the total amount of the pie that you have is going to be 1/30 plus, or 1 plus 3 plus 2/30, which becomes 6/30 of the pie. So similarly here, we have 1 over 30 ohms plus 3 over 30 ohms plus 2 over 30 ohms. That's 6 over 30 ohms. But remember, that's not our equivalent resistance. That's 1 over our equivalent resistance. So we have 1 over equivalent resistance equals 6 over 30 ohms. So to isolate for equivalent resistance, you just need to flip both sides. You need to take the inverse of both sides. After all, it's just a mathematical operation. Whatever you do to one side, you got to do to the other. So to get Req on the top, but we invert the left side, well, that means we need to invert the right side as well. That becomes 30 ohms over 6, and that's the same thing as 5 ohms. So great, the equivalent resistance of our circuit is 5 ohms. So if we wanted to find the current coming out of the battery, we would say that the battery voltage is equal to the current coming out of the battery times the equivalent resistance of the circuit. Now I'll tell you now, it's actually not necessary to figure out the current coming out of the battery in this particular problem. I'm just doing it because it's good practice to do that in general. After figuring out equivalent resistance, figure out the current coming out of the battery using a quick application of V equals IR. So solve for the current coming out of the battery. That's equal to the voltage of the battery divided by the equivalent resistance of the circuit. So 27.5 volts divided by 5 ohms. That's 5.5 amps. And notice I did not put a box around this. This is not the answer to any problem. Actually, the equivalent resistance wasn't either, but I figure that's everybody always needs to know that. So might as well put a box around that, which I did in the previous slide. So next, we use the fact that because this is a pure parallel circuit, the voltage gain given by the battery is equal to the voltage drop across each arm of the circuit. In other words, you start at 27.5 volts at the very beginning, you go down a certain number of volts, and you must end up at 0 at the end. Well, you only go down once. It's like you have your river, it splits into 3 different branches, but each branch goes down a waterfall that goes from the top to the bottom of the same cliff. It's not like a series circuit where it's like you have 3 separate waterfalls, one of them from the top of the cliff to the middle of the cliff, one of them to the middle of the cliff from the middle of the cliff to somewhere above the bottom, and the last from somewhere above the bottom to the bottom of the cliff. Here, they all go down at the same time. In other words, you have the same drop in height in the waterfalls all at once, and voltage is very much like height. In fact, voltage is called electric potential, and height is like something called gravitational potential. So they really are analogous to each other. So you go down all 27.5 volts all at once, no matter which resistor you go through. So there's a voltage drop of 27.5 volts in each resistor. So that's all there is to it. So the voltage drop is the same across every arm of a parallel circuit, just as the current is the same through every resistor of a pure series circuit. Here, the current is not the same because the current splits multiple different ways. Let's figure out how it splits up. Well, that's what we're going to do here. So the current splits up 3 different ways. So I'm just going to rewrite our givens just to remind us what our givens were. So I'm going to figure out what I1, in other words, the voltage through the 30 ohm resistor, and I2, the voltage through the 10 ohm, or the current through the 10 ohm resistor, and the current through the 30 ohm resistor, I should say, was I1, and I3 is the current through the 15 ohm resistor. So I'm just going to call them I1, I2, and I3 from now on. So we do V equals IR, which means I equals V over R, just divide both sides by R, and there we go. We just do I equals V over R 3 times. In this case, each time the V is 27.5 volts, but the R is whatever the resistance of the circuit is, or sorry, the resistance of that particular resistor is. So upon doing that, we get 0.917 amps and 2.75 amps and 1.833 amps. And in case you're curious, I'll just tell you, if you were to add these 3 currents together, you would end up getting, well, 5.5 amps, which was the current that we calculated as coming out of the battery. So that works out. In other words, this 5.5 amps coming out of the battery splits up into 0.917 amps going this way, and 2.75 amps going this way, and 1.833 amps going this way. So now there's only one thing left to do: calculate the individual powers dissipated by each resistor, and we end up getting 25.2 watts through the 30 ohm resistor, 75.6 watts through the 10 ohm resistor, and 50.4 watts through the 15 ohm resistor. Notice that if you remember the previous video about the same circuit, except with all of these resistors being in series instead of parallel, that the total power in that circuit was, I think, less than even the smallest power in this circuit. A parallel circuit is going to dissipate a lot more power than a series circuit composed of the same resistors, which means the battery is going to drain much, much more quickly in this case. In fact, the total power in this case is 151.25 watts, so that's going to drain the battery like 10 times as quickly or so as if all these three resistors were just in series, when the current coming out of the battery would be a whole lot less. So it's just something to keep in mind in terms of power consumption by a battery. So that's how you can calculate the current and voltage drop and equivalent resistance and resulting powers through the resistors for a pure parallel circuit. So next we're going to move on to a slightly more complicated circuit, a hybrid circuit. Thank you.